Radiation inversions. Radiation inversions typically form on calm, clear nights where the ground is able to radiate efficiently and effectively, and hence become much cooler than the air a few meters above it. Radiation inversions often form on nights where there's a subsidence inversion, because the inhibition of mixing across the subsidence inversion produces calm winds, and oftentimes if there's not sufficient moisture, then the nights will be clear. The inversion base is usually at ground level, while its strength and depth depend upon a number of factors, including the rate and duration of cooling. So the stronger the cooling and the longer it lasts, the stronger the inversion will be. The wind speed. The radiation inversion occurs because the ground cools radiatively via long-wave radiation, and the air just above it is in direct thermal contact, and so the air cools as the ground cools. If the wind is too strong, then that air at the surface will mix with warmer air aloft and will inhibit the cooling. But if you want to produce a deep inversion, then you do want a little bit of wind to mix that through, just not too strong. Cloud cover and water vapor act to absorb infrared radiation and inhibit the long-wave cooling. Again, on nights where there's a subsidence inversion, the wind speed is typically low, and if there's not a lot of moisture, then the water vapor content is low and there's not much cloud cover. The wind tends to convert a radiation inversion to a turbulence or mixing inversion with its base some height above the inversion, as near the surface you establish a dry adiabatic lapse rate. Here's an example of a radiation inversion below a subsidence inversion at about 820 hectopascals, and the radiation inversion goes up to about 950 hectopascals in this case. You can see in the bottom left that there's a high in the Tasman Sea ridging across Victoria, producing a light northerly drift at the surface, and the cloud image shows that it's largely cloud-free over the Melbourne area. You can see that associated with the radiation inversion is cooling as you move down towards the surface, but moistening and increased surface dew point temperature, and that's because the moisture in the air isn't mixed by strong winds, and so it collects at the surface. Here we have another radiation inversion. You can see it's associated with a high in the southern Tasman ridging over Victoria. There's a very strong radiation inversion below a weak subsidence inversion, and the radiation inversion is very clear in both the dew point profile and the temperature profile. As described in the last slide, the dew point should increase as the inversion strengthens, as the winds are weakened and can't mix the moisture through depth. But then, as you can see in the sequence of metadata here, from 2030 UTC to 2300 UTC, which is the time of the trace, that as the temperature decreases, so the dew point is decreasing, and that's because dew starts to form. And then at sunrise, the temperature starts to increase again, and you see an increase in the dew point temperature as liquid water is evaporated. Of course, again, during the day, the dew point temperature might decrease due to mixing aloft. Our last example shows a large high over southeastern Australia and cloud-free conditions, as you can see from the satellite image. In the trace for Cobar, you can see a subsidence inversion again above 900 hectopascals and a low-level radiation inversion. And if you look at the sequence of metadata, you can see winds are calm at the surface right through from 2000 to 2220, and conditions are cav okay initially, so cloud and visibility okay, visibility greater than 10 k's and no cloud below 5,000 feet, and the temperature and the dew point are the same. 16 minutes later, there's fog in the vicinity with a visibility of 3,000 meters, and that persists until 2100, where there's fog patches with a visibility of 8 kilometers, and then again fog in the vicinity with visibility to 1,500 meters at 2110, and you can see during this time the temperature and the dew point have dropped together. That is, the air has become cooler and the vapor is being turned into fog. That's why the dew point's decreasing. Fog conditions, which is visibility below a kilometre at 2130, and then you can see slowly the temperature and the dew point rising together until by the time we get to 2220 they've come apart by degrees Celsius, and conditions are again cav okay.